Yes, and Weiran Shen is an assistant professor at Gaolin School of Artificial Intelligence of Renmin University. And Weiran obtained both her bachelor's degree and her PhD, his PhD degree from Tsinghua University. And he also had a postdoc at Carnegie Mellon University. His research interests include multi-agent system, game theory, mechanism design, and machine learning. And he has served as PC and SPC for a number of conferences in this area. Also, his research in mechanism design has already been adopted by online advertising platforms such as Baidu and ByteDance, and including Baidu's revenue by about 5%. So, Weiran, thanks for joining us. Go ahead.
All right. Thank you for the nice introduction, and thank you for having me here. Really happy to have this opportunity to be here to talk about our recent work. So today I'm going to talk about the inverse game theory for Stackelberg games, the blessing of bounded rationality. This is a joint work with Jibang from the University of Chicago, Fei from Carnegie Mellon University, and Haifeng also from the University of Chicago. And in this work, we consider Stackelberg games and studied the problem of recovering the payoff matrix by by observing the equilibrium behaviors of both players. So the interesting thing in this work is that we assume that both players have bounded rationality. So this kind of bounded rationality behavior model usually makes things more complicated. Actually much more complicated if you are going to compute the equilibrium of a certain game. But the interesting thing is that in our setting, this bounded rationality behavior model actually enables us to recover the underlying payoff matrix of the game, and we indeed we actually utilize this kind of bounded rationality to recover the game parameters. So let me first briefly talk about why we studied this problem. So in game theory, our goal is usually to predict the player's behavior according to some kind of solution concept, assuming that we're given the game setting, which may contain the game payoff matrix for both players, or the type distributions if the game itself is Bayesian. But in reality, this rarely happens. For example, in e-commerce platforms, the sellers usually does not know the customer's preferences, but he can observe the customer's behaviors. For example, what kind of items the customers have looked into, what kind of items they have put in their shopping cart, or what kind of items they have already bought before. And another example is the security domain. So in the security domain, there are usually a defender and some attackers. The defender usually does not know the attacker's real utilities, but gets to observe the attacker's responses to the defender's actual defense strategies. So this kind of difference between theory and practice motivates an interesting research topic called the inverse game theory. So as I just mentioned, that the goal of game theory is to prescribe the player's equilibrium behavior given all the game parameters. But The inverse game theory does exactly the opposite. We're given the player's equilibrium behaviors, and our goal is to recover the underlying game parameter. So the question we're going to study in this work is that given all the equilibrium behaviors, what kind of game parameters can actually induce such behaviors? We focus on the Stackelberg setting. So in a Stackelberg game, there are usually two players. One is called the leader, and the other called the follower. So the leader will move first by committing to a certain strategy, and then who will just announce this strategy to the follower, and then the follower will respond to the leader accordingly. So you can model this game as a kind of extensive form game. So this kind of Stackelberg game model has been widely adopted in a lot of areas. For example, in security domains, the defender wants to protect a number of targets, while the attackers wants to attack these targets. The defender first announces his defense strategies, and then the attackers will try to pick the best target to attack. And so here are some of the notations that I'm going to use during my talk. I'm going to use U to denote the leader's payoff, and V to denote the follower's payoff. Both of them are matrices. So here the lowercase m is just the number of available actions to the leader, while the lowercase n is just the number of actions available to the follower. Therefore, the leader's strategy is just a probability distribution over a set of available actions to him, which can be represented as a point in delta m. And similarly, the follower's strategy is also a point in delta n. So in our setting, we assume that the leader can choose any kind of mixed strategy. And then after announcing this strategy to the follower uses the Quantal response instead of the usual best response. So if the follower is fully rational, he will choose the action that could give him the highest possible utility. But we assume that the follower is not fully rational. It's so he will use the he only has bounded rationality. In particular, we choose to use the Quantal response model. So in the Quantal response model, the follower's strategy is purely is always a randomized strategy. So the probability of choosing a certain action J is proportional to e to the lambda times the expected utility of choosing that action. So it can be written as a formula here. So if you are familiar with neural networks, it's essentially the softmax function. And here the lambda is just the rationality constant. So if lambda so here lambda is always a non-negative number. So if lambda is 0, then the follower would choose any action uniformly randomly. And if lambda goes to infinity, then the follower becomes fully rational. Okay. So our research question is, can the leader recover the underlying payoff matrix of the follower by querying the follower's response with certain chosen X? So here we assume that once the leader choose a certain mixed strategy, the leader is actually querying the follower for the follower's actual response to that strategy X. So I would like to so compare the quantum response and the best response behavior model. So in the best response behavior model, the follower will always use the deterministic strategy. In this case, computing the optimal leader strategy is simple. You just solve the problem by solving a series of linear programs. But if the follower uses quantum response, then finding the optimal leader strategy can be difficult. But if the follower uses best response, or if the follower is fully rational, then recovering the follower's payoff is actually very difficult. This is because if you this is because if the leader queries a certain strategy X, then the response of the follower is deterministic. It always gives the same response if the query is the same. So it does not actually give you any information about the neighborhood of this X. And but this is different in quantum response models. In quantum response models, the follower's response is non-deterministic, and if you query the same X for a lot of times, then they will give you the empirical frequency of the follower's response is going to tell you something about not only the point of X itself, but also the entire neighborhood of X. So this is why under the quantum response assumption, we are able to recover the follower's payoff. Before I present our main result, I need to talk about the identifiability issue. This is because in quantum response behavior models, the follower's strategy will stay the same if we translate the follower's payoff matrix by a certain vector. So what does that mean? So if you look at the quantum response model, this response model here, X is a vector, and Vj is jth row of the matrix V. So if you take a row-wise translation, then this kind of V here, every single element of this vector V here will be translated by a constant. Then the resulting behavior of the follower will just stay the same. So in this case, even if you are able to so if you find a payoff matrix that is just a row-wise translation of the original of the underlying payoff matrix of the behavior of the follower, then they will give you exactly the same follower behavior. So to tackle this problem, we introduced the logic distance. So here, the logic distance is defined as follows. We introduce a vector z here to capture the row-wise translation. So if the distance between the underlying payoff matrix and the recovered payoff matrix is different by a certain constant vector, then we say that okay, we have already perfectly recovered the payoff matrix of V, because they will give you exactly the same follower behavior. Okay. So first, let's consider a simple a simple case. This is also a very ideal case. We assume that for every query, the follower will tell us his exactly mixed strategy Y instead of just an action that is sampled according to the strategy Y. Okay. In this case, we're able to get the actual mixed strategy of the follower, and in this case, we can perfectly recover this follower's payoff matrix with m linearly independent queries. Here, m is the number of actions available to the leader. So how do we do this? So let's assume that we have a guess of the underlying payoff matrix V tilde, and if V tilde, given this V tilde, we can actually predict the response Y tilde of query X, and then our goal is to find a V tilde that can match Y tilde and the actual Y. So so here Y tilde is our prediction, right? And Y is the observed mixed strategy of the follower. So if we can somehow find a V tilde that makes these two things equal, then we say that we can perfectly recover the payoff matrix V. So how do we do this? How do we match these two strategies? Notice that these two strategies are actually probability distributions. Then we can try to minimize the cross entropy between the predictions Y tilde and the actual mixed strategies Y. So here is just the cross entropy between these two strategies. And if you do the math, you can get the following optimization program. We introduce an additional variable here, which is ZT. So here, T is the T's query of the leader. So so XT is the T's query of the leader, and ZT is just a linear transformation of XT. So so the objective function, the first term of the objective function is just a log sum exp function, which is a convex function of z. And the second term is also linear, and the constraint is also a linear constraint. So which means that the problem itself is a convex problem and can be efficiently solved. And in fact, this optimization program, the only variable we care about is V tilde, and Z is just an auxiliary variable we introduced to make the formula look beautiful. Okay, and so this is a simple case where we can get mixed strategies directly from the follower. But what if we can only get the realized actions instead of the actual follower strategy? So in this case, every query X would just give us an action Y that is sampled from the quantum response model. Okay, so the first idea is that we can use the maximum likelihood estimation to find the underlying parameter or underlying payoff matrix of the follower. So, but this kind of method is difficult to optimize, because if you want to maximize a lot of, if you have a lot of queries, you need to maximize a very long, a very large objective function, the likelihood function. And then also it could be difficult to bound the error of the estimation. So our idea is to use the previous result. We try to get if we are able to get the actual followers quantum response for m different queries, we are able to recover the underlying payoff matrix. So we decompose the problem into two smaller problems. The first problem is that we try to estimate the mixed strategy of the follower by querying a certain point multiple times. And the second problem is to use this estimated mixed strategy to estimate the payoff of the follower. And we can, if we can actually bound the error of both steps, and then we can combine these two bounds to get the final bound for the recovered payoff matrix. So okay, so for the first step, we have this kind of result. So it says that for any query X, let Y be the underlying quantum response, and with this kind of with this amount of samples of with this amount of queries of X, this is actually the repeated queries. So we query the same X for a lot of times, and then hopefully the follower will give us a lot of sampled actions from his quantum response, and we use the empirical distribution Y, which is just the empirical the frequency of choosing each action, to estimate the actual to estimate the actual response of the follower. And clearly, if the number of queries goes to infinity, the frequency of or the empirical distribution y hat will converge to the actual quantum response model. And we prove that with this kind of with this amount of queries, we are able to get a 1 minus epsilon approximation of y with probability at least 1 minus delta. Okay, so the proof is based on the mainly based on the Chernoff multiplicative bound, which bounds the relative error of the estimated quantum response. So I guess I don't have time to go over all the proofs, so I'm going to skip these slides. And for the second step, we're going to use the estimated follower strategy to recover the underlying payoff matrix V. And here we say this result says that if we have m queries of 1 minus epsilon multiplicative approximations of the followers mixed strategies, then we are able to recover the underlying payoff matrix V within the logic distance, which is of O over O of epsilon over lambda. Here, lambda is a rationality constant. So you can see that if we are able to recover, if we are able to estimate the followers mixed strategy within this 1 minus epsilon error bound, we are able to recover the underlying payoff matrix with high quality. Okay, so yeah, so if we combine these two results, we get our final result, which is that if we can query the same X multiple times, we can get a very good estimate of the underlying payoff matrix. So okay, I just skip these results here, and so these two results are for recovering the underlying payoff matrix. But what if we're going to use this recovered payoff matrix to play against the follower. So since we can recover the underlying followers payoff matrix with very high quality, we can actually use this recovered payoff matrix to compute the optimal leader strategy. And we show that under certain technical conditions, we are able to actually construct a near optimal leader strategy for any V within and that is for any V that is within a distance from V of this amount. So this means that if we can recover the followers payoff matrix, we are able to with high probability we are able to bound the we're able to bound the utility loss by this amount. So yeah, that's the main result of this work. So let me summarize. So we consider an inverse game theory setting, and we try to recover the underlying followers payoff matrix by querying the followers mixed strategies. And we also give a sample complexity of estimating this followers payoff matrix. And so if you think about the whole recovering process, you can find that this kind of process is a bit I would say it's a bit stupid, because we just randomly choose these m different leader strategies, and then query these strategies multiple times to get an estimation of the followers' response. And one of the interesting future work is that can we somehow choose these queries in a more clever way, so that we don't need to stick to these set of queries for a long time. And another interesting future work is to consider more general settings rather than the Stackelberg game, and also consider the some other boundary rationality model beyond this kind of quantum response model. Okay, thank you for your attention. Any questions?
Thank you, Weiran. Thank you for summarizing the interesting aspects of inverse game theory that you need to learn payoff functions. So Xiaoming, go ahead. I think you have a question.
Yes, Weiran, very nice talk. Actually, your talk reminds me joint work with Professor Chen and also Xiaohui. I think in that work we studied it's the Fisher market model. We also each day we propose a price and to learn the parameter. Actually, we would like to learn the equilibrium. I think there's some relation. So my question is, so here is it possible to extend this study to more complex game like Fisher or LW? And also your utility function right now is just one kind. Is it possible to extend the utility to more general functions? Thanks.
Okay, next question. I think I haven't thought about those particular game models, but my guess is that if you want to recover the game parameters, you probably still need to assume some kind of boundary rationality for those players, because if the as I just mentioned, if the players are fully rational, they won't give you much information on the game structure itself. it just gives you the response of that particular point, and you don't get anything from this response. You don't get any information about the local areas. So I guess, yeah, if we can, if you want to actually recover the game structure, you probably still need these kind of boundary rationality model. Hopefully, or ideally, you can parameterize this behavior model and only learn some kind of small amount of parameters. That would be much easier.
Okay. Thanks. Yeah.
Thank you for the
question.
question.
I like to follow up. So Weiran, in your model, you try to learn the leader trying to learn followers payoff function or payoff matrix, right? So what if the leader also want to learn while optimize, right? He want to optimize for his own payoff.
Yeah, that's if I understand your question correctly, you're saying what if the leader also wants to optimize his strategy during the learning process? Or try to minimize the regret it's going to suffer. Yeah, that's a very interesting question. Let me actually this is a third bulletin here. The future work is just trying to say exactly the same thing as you just said.
Okay.
Actually, we're already working on this problem and have already got some preliminary results. And what I can tell you is that we can formulate this problem as a something similar to a linear bandit problem, and then we can apply those the algorithm for the linear bandits to this setting and get hopefully get a nice regret bound.
Great. Looking forward to your result. So good. Let's conclude our first session.